Today we're going to be talking about how to find the acute angles between two curves, and in this particular problem we've been given two curves represented by the equations y equals x squared and y equals x cubed. Now if you've already watched my video about finding the acute angles between two lines, you have a leg up on this video already because the process we're going to use for finding the angles between two curves is going to be really similar to the process for finding the angles between two lines. The only difference is when we were finding the angle between two lines, it was really easy because if you can picture, just as an example here, if you can picture two lines like so, maybe graphed on an XY coordinate system, we're looking for the acute angle here between the lines. This is going to be the acute angle between these lines. It's really easy to represent these lines with vectors and use our corollary formula for cosine of theta. But how do we find the acute angle when we have two curves? It's not just straight lines. It's not as easy as finding the angle between lines. Well, when we talk about finding the acute angle between two curves, really all we're saying is that we're looking for the angle between the tangent lines to these curves at their points of intersection. So in that way, it really simplifies to an angle between two lines problem instead of an angle between two curves problem. The only difference is that we have to do two steps before we can just look for the angle between two lines. The first thing we need to do is find the points of intersection of these two curves. We need to figure out where they intersect one another. Then we need to find tangent lines to these curves at any points of intersection. Then we've really simplified it to finding the angle between lines because we'll have equations of the tangent lines and we can just find vector representations for those lines and then the angle between those vectors. So let's get right to it. What we're going to do first is find the points of intersection of these two curves. Because both curves are equal to y, we can set the right-hand sides equal to one another and say x squared is equal to x cubed. Well, for which values of x is this equation true? The only time this is going to be true is if x equals 0. That makes sense, right? 0 squared is equal to 0 cubed. 0 equals 0. That's fine. Or when x is equal to 1. 1 squared is 1. 1 cubed is 1, right? Negative 1 wouldn't work because we get positive 1 on the left-hand side, negative 1 on the right-hand side when we cubed it, and this equation wouldn't be satisfied. The only points, the only x values for which this equation works is when x equals 0 and x equals 1. Now that we have these values, we need to plug them both back into our two original equations to figure out where we have points of intersection. So what we're going to do is we're going to take x equals 0 first, and we're going to plug it into y equals x squared. So let's make a little chart here. Let's make a little chart like this. And we'll say y equals x squared, and then we'll say y equals x cubed, like so. And we'll divide these. Now when we plug x equals 0 into y equals x squared, we just get y equals 0. When we plug x equals 0 into y equals x cubed, we get y equals 0. So because we got the same value here, we got y equals 0, there's really only one coordinate point. From this row, we take an x value of 0, and we take a y value of 0. It's possible that we could have gotten two different values for y. If we had two different values for y in this row, that would mean that we would have two coordinate points, both with an x value of 0, each with a different y value depending on our results here. But because the y values are the same, we just have one coordinate point, 0, 0. If we take x equals 1 and we plug it into both of our original equations, here we're going to get y equals 1. Here we're going to get y equals 1. Again, we have the same y value. So from this row, we'll take the x value, which is 1, and then the y value, in both cases we got 1, and we have a coordinate point of 1, 1. Again, we could have gotten different y values, which therefore would have resulted in two different coordinate points here. But whatever results we get here, these are our points of intersection. These are the coordinate points where our functions, our curves, y equals x squared and y equals x cubed, intersect one another. What this tells us now is that we need to find tangent line equations for both of these curves at both of these coordinate points. So just so I don't get lost, what I like to do is make another chart. I'm going to take my points of intersection, 0, 0, and 1, 1, and put them over here on the left-hand side of my chart. And then across the top, I'm going to write my two equations, y equals x squared and y equals x cubed. And I'm going to make a chart like this. What this tells me, I have 4 boxes in my chart I need to fill in. I need to put an equation for a tangent line in each of these 4 boxes. So in this upper left-hand box here, what I'm going to do is find the equation of the tangent line to y equals x squared at the point 0, 0. So hopefully you remember how to find the equation of the tangent line at a specific point. Remember that what we do first is take the derivative of our function. So our function's y equals x squared. We use the power rule and we get y prime is equal to 2x. That's our derivative of this first function here. If I take the derivative of y equals x cubed, again I use power rule, and I get y prime equals 3x squared. These are my 2 derivatives. Now, what I need to do is take my point of intersection and evaluate it in this derivative function. So I'm going to say y prime of 0, 0. This is going to give me the slope of my tangent line at the point 0, 0. I get 2 times 0, or just 0. And over here in my second derivative equation, if I plug in my point of intersection 0, 0, I'm going to get y prime of 0, 0 is going to be equal to 3 times 0 squared, or just 0. Remember that the equation of the tangent line, I'll go ahead and write it here in my reminder section. The formula for the equation of any line, in point slope form, will be y minus y sub 1 is equal to m, the slope, times x minus x sub 1, like this. What this is, remember, I plug my slope in here, my slope at the point of intersection, and then I have my coordinate point here, x sub 1 and y sub 1. Well, here I have a slope of 0 and a point 0, 0. So what I'm going to get is y minus 0 is equal to the slope 0 times x minus the x value of my coordinate point here, 0. When I simplify that, I'm going to get y on the left-hand side and just 0 on the right-hand side, because this 0 is multiplied by everything, x minus 0. So y equals 0 is my tangent line equation for this box here, y equals 0. If I go over here to the right, again, I'm going to do the same thing. I have a slope of 0, a coordinate point of 0, 0. I'll get y minus 0 equals 0 times x minus 0. And when I simplify, I'll get y equals 0. That's going to be my tangent line equation for this box here. Now I need to do the same thing with the coordinate point 1, 1. I need to plug that into my derivative equation. So here, y prime of 1, 1, I'll get 2 times 1, or just 2. If I plug it into my other derivative equation for y equals x cubed, I'll get y prime of 1, 1 is equal to 3 times 1 squared, or just 3. I'm going to use my formula for the equation of the line again. I have my slope, 2 and 3, and my point, 1, 1. So for this one, I'll get y minus 1 is equal to 2 times x minus 1. And if I simplify that, I get y minus 1 equals 2x minus 2. Adding 1 to both sides, I'll get y is equal to 2x minus 1. If I do the same thing over here, I'm going to get y minus 1 equals 3 times x minus 1. Simplifying, I'll get y minus 1 equals 3x minus 3. And then adding 1 to both sides, I get y equals 3x minus 2. These are my tangent line equations for each of these functions at the point 1, 1. So y equals 2x minus 1 and y equals 3x minus 2. Now, essentially, I'm looking for the angle between these two lines, y equals 0 and y equals 0, because these are my tangent line equations at the point of intersection here, 0, 0. So what's the angle between the line y equals 0 and y equals 0? Well, in this case, it's the exact same line, and because it's the exact same line, the angle between them is 0. Well, how do I prove this to myself? I'll show you how I prove it to myself, and then we'll use the same process to find the angle between these other two tangent lines at the point 1, 1. The first thing I want to do to prove it is to find a vector representation for this y equals 0 line here. Well, what we want to do is have our y and x terms on the left-hand side equal to some constant. So really what we can say is that this equation y equals 0 is 0x plus y equals 0. When I have it in this form with my x and y terms on the left-hand side equal to some constant, I can pull out the component values from this equation, and that's just the coefficients on our x and y terms. So the coefficient on my x term is 0, and the coefficient on my y term is positive 1, so my vector then is 0, 1. Same thing obviously here, since it's the exact same equation, I'm going to get the vector here 0, 1. When I have two vectors, notice we're going to be using this corollary formula for cosine of theta. I just need the dot product of these two vectors and the magnitude or the length of these two vectors. Well, my dot product, remember, if we call this vector A and we call this vector B, we're going to say the dot product of A and B is going to be equal to the sum of the product of each of our components. So we say the x component here of A, which is 0, times the x component of B, which is 0. So we say 0 times 0. And we add to that the product of our y components. Both of those are 1, so we say 1 times 1. Our dot product then is 0 plus 1, or just 1. Now I need the magnitude of A and B, or the length of each of those vectors. Well, really, I just take my component values, and we use the distance formula. Let's calculate first the distance of A. It'll be the same for A and B because it's the same vector. So I'll say the distance of A, distance formula of the vector A, is going to be the square root of my component value. So I'm going to take the x component 0 and I'm going to square it, and then I'm going to take the y component and square that also and add it to the square of the x component. So 0 squared plus 1 squared, I take the square root, I'm going to get the square root of 0 plus 1, or just the square root of 1, and that's equal to a positive 1. That is the magnitude of A. Because my vectors are equal, it's also the magnitude of B. So in order to find the angle between these two vectors A and B, all I do is say cosine of theta is equal to the dot product of A and B, which I already know is 1, divided by the magnitude of A, which is 1, times the magnitude of B, which is also 1. I have 1 over 1, or cosine of theta is equal to 1. Now at this point, you should just know this off the top of your head, but if you don't, and you won't for this second example, you'll need to use your calculator. You need to make sure that it's set to degree mode. When we're looking for the angle between curves or the angle between lines, we want to make sure that we're set to degrees instead of radians. Then you're going to do theta is equal to the inverse cosine function, or arc cosine, or cosine to the negative 1, of 1. When we take arc cosine of both sides of this equation, we get cosine to cancel on the left, so we're just left with theta on the left-hand side, and we get arc cosine of 1 on the right-hand side. This, of course, is just equal to 0, so we get theta equals 0. And of course, that should make sense to us, because when we have two lines that are exactly the same, y equals 0 and y equals 0, the angle between them is just 0. They're not offset from one another. They're not skew from each other at all. It's the same line. So the angle is 0. So that's the process we're going to follow. It'll be more applicable when we look at this second example here, and we can do that easily. So again, our component values here, if we transform this equation so we have our y and x values on the left-hand side, we'll subtract 2x from both sides and we'll get negative 2x plus y is equal to negative 1. We have our x and y values on the left and a constant on the right. And so what that's going to give us is the coefficient on x of negative 2, the coefficient on y of positive 1. So there's our vector representation. Over here, for this tangent line equation, we'll move 3x to the left-hand side by subtracting 3x from both sides. We get negative 3x plus y is equal to negative 2. X and y is on the left, just a constant on the right-hand side. And so we take our coefficients and we get negative 3 and positive 1. These are our two vector representations. Now, if we use different variables here and we call this C and we call this D, the dot product of C and D is going to be equal to the product of our x components, negative 2 and negative 3, plus the product of our y components, 1 and 1. When we simplify, we're going to get positive 6 plus 1, which is a positive 7. Now, we just need to find the length of each vector, so we'll say the distance formula d sub c. To find the length of c, we'll just do the square root of our component values squared. So negative 2 squared plus 1 squared. We took the x component and the y component of this vector, negative 2, 1. And that's going to give us the square root of negative 2 squared, which is 4, plus 1 squared, which is 1. 4 plus 1 is 5, so we get the square root of 5. If I do the distance of d, or the length of d, I'm going to do the square root of the square of each component and then the sum of those. So negative 3 squared plus 1 squared, like this. I'm going to get negative 3 squared is 9, 1 squared is 1, 9 plus 1 is 10, so just the square root of 10. That's the length of my vector d. So now to find the angle between these two lines, or the angle between these two vectors, I'm going to say cosine of theta is equal to c times d divided by the magnitude of c times the magnitude of d, which is going to give me my dot product, 7 in the numerator, divided by square root of 5 times square root of 10, which is going to be cosine of theta equals 7 over square root 50. I want to solve for theta by taking the inverse cosine function of both sides, and I'll get theta equals arc cosine of 7 over root 50. Again, when my calculator is in degree mode and I calculate this, I get a value. Theta is approximately equal to 8.1 degrees if I round a little bit. So 8.1 degrees is the angle between these two tangent lines, which essentially we'll call the angle between these two curves at their point of intersection, 1, 1. So when I write my final answer, what I really want to say is that my angle is 0 degrees at the point 0, 0, and my angle is approximately 8.1 degrees at the point 1, 1. These are the acute angles between the curves.